Hi. In previous videos, we have studied sampling of a band-limited signal by an impulse train. So let us remember how we use sampling and how afterwards we reconstruct the original signal from the samples of the signal. So let us start with a signal x of t, which is band limited. It's a band limited signal. So this means that x of omega is equal to 0 for absolute value of omega greater than some omega constant, omega m. So omega m is the highest frequency component in the spectrum. So x of omega vanishes outside the band of frequencies extending from minus omega m to omega m. Okay, we define the impulse train P of t as m from minus infinity to plus infinity, delta of t minus m ts. So here ts is the sampling period, and we define the sampled signal xs of t as the product of x of t and p of t. Now, in previous videos, we have seen that if we evaluate the Fourier transform of xs of t for omega s, which is equal to 2 pi over ts, for omega s greater than 2 omega m, the Fourier transform of xs of t will be composed of shifted replicas of x of omega in the frequency domain. Okay, so in time domain we are doing the following. In fact, we have, suppose that let us show this graphically. We have a certain x of t, the signal x of t, and then we have the impulse train p of t, which is given over there in terms of the expression delta of t minus mts, and m is running from minus infinity to plus infinity. So xs of t, if we plot xs of t as a function of t, we have sampling by impulses. So we have this impulse at t equal to 0. Then at t equal to ts we have this impulse. Then at 2ts we have another impulse. And we have an impulse here. So we have, in a way, the envelope is defining the graph of x of t. So we have these impulses weighted by the values of x of t at the points where the impulses strike. So these time instants are 0, ts, 2ts, minus ts, etc. and etc. in both directions. That means as t tends to larger positive values and t tends to negative values. Okay, we have sampling with the impulse train. Okay, it is obvious that in real-world applications we are unable to construct such an impulse train. That means pulses with zero duration and infinite magnitude. These are not physically realizable. So sampling by the impulse train is not physically realizable. So sampling by impulse train is not realizable. In other words, we cannot form the signal which is the impulse train, the periodic repetition of impulses, and impulses are impossible to realize physically because they have zero duration and infinite magnitude. So therefore, sampling by the impulse train is only a mathematical model for sampling. Okay, in reality, how can we obtain a sample signal? We can do the following. At each sampling instant, by sampling instance we mean all those positive and negative time instants. That means ts, 0, ts, minus ts, 2ts, minus 2ts, etc. So we do the following. We define a signal which is called the sample and hold signal, or zero order hold signal. So we can apply a sampling operation in the following form. We just measure the value of the signal and keep that constant value for ts time units, and then measure again and again, keep it for the next ts time units. Okay, so this is called the sample and hold approach. The sample and hold approach, sometimes this is called zero order hold approach, is simply the signal defined as follows. Is the signal, let us call it XZOH, zero order hold, defined as okay, X sub zero order hold, okay, this is Z of T is defined as follows. It is M running from minus infinity to plus infinity x of mt h sub z o h again t minus m ts, where h z o h of t is defined as follows. It is equal to 1 for t between 0 and ts, and 0 otherwise. In other words, h sub z o h of t is a rectangular pulse which is equal to 1 from 0 to ts and 0 otherwise. And in the signal x sub z o h of t, we have samples of x of t multiplied by shifted versions of this h of z o h of t. So in other words, we are representing now the signal x z o h of t as shifted replicas of the rectangular pulse multiplied by the weights, which are just the samples of the original signal x of t. So x z o h of t is in fact the following signal. So we sample the value of x at t equal to 0 and keep it for ts time units, and then we take the sample at ts and keep it for the next ts time units, so up to 2ts, and then sample again and keep it for the next ts units up to 3ts, and so on. Similarly, we do this for all time samples. Okay. So the signal obtained by the sample and hold approach is defined by using the samples of the signal multiplied by shifted replicas of the rectangular pulse of duration ts, and we obtain again a kind of sampled signal. Okay. Now you see that this signal can be realized, can be obtained by using electronic hardware, some kind of circuitry. So x z o h of t is physically realizable. Okay, but also we remember that we have developed the sampling theory in terms of sampling by the impulse train. Okay, so how can we use that information in the analysis of the signal, which is obtained by the sample and hold approach. Okay, so this is our first question. And then we ask the following second question. Are we able to retrieve the original signal x of t from the signal x sub ZOH of t? Okay? So let us try to answer these questions. Okay, now we have xs of t equal to the sampling by the impulse train, x of t, x of m ts, delta of t minus mts, and we have okay, this is the band limited signal x of t sampled by the impulse train, but we have just mentioned that this is not a physically realizable signal. So the physically realizable signal is the so-called sample and hold, the signal obtained by using the sample and hold operation, or the zero order hold operation, and that signal is again obtained in terms of the samples of the original signal x of t at the sampling instance mts multiplied by h of t minus mts. So here h is a very well behaved function, and we have defined h of t as the rectangular pulse which is equal to 1 from 0 to ts and 0 otherwise. Now we ask the following question: can we obtain xZOH of t from xs of t by means of a certain operation? In fact, consider a linear time invariant system whose impulse response is h of t. Consider a linear and time invariant system whose impulse response is h of t. So if we apply xs of t as the input signal to this system, we are going to obtain xZOH of t at the output. Okay, so we have the linear time invariant system with impulse response h of t, and if we apply xs of t as the input signal, the output will be the zero order hold, the signal we obtain by zero order hold. Okay, here just to avoid confusion, I have to explain the following. In fact, this is only a model, mathematical model for obtaining the zero order hold signal. In fact, the zero order hold signal ZOH of t is obtained very easily by means of some hardware by just measuring the value of the signal at a specific time instant and keeping that as the constant value for the following TS time units and repeating this for every sampling time instant. Okay? Now, how do we obtain the output as x of z or h of t for this configuration? Because we know that delta of t will give us h of t. If we apply an impulse at the input, the output is h of t. So delta of t minus mts will give us h of t minus mts by time invariance. Okay, a shifted impulse will give us the shifted impulse response with the same shift, time shift. Okay, so x of mts delta of t minus mts. Okay, let me write it here. X of mts delta of t minus mts will give us the output x of mts h of t minus mts. Okay, this is due to both time invariance. Shifted impulse gives us the shifted impulse response, and when we weight the shifted impulse by x of mts by linearity, we have the same weight appearing at the output. And again by linearity, if we have the summation over m, x of mts delta of t minus mts will give us x of mts h of t minus mts. Okay, in other words, this is xs of t. The input xs of t will give the output x sub zoh of t. Okay. So the block diagram for the mathematical model of the sample and hold approach is the following. We have x of t. We multiply x of t by the impulse train p of t. In fact, we are not doing this in reality. This is only the mathematical model because we want to use the theory we have developed for sampling by the impulse train, and then we obtain xs of t, and this xs of t is fed as the input signal to our LTI system with impulse response h of t, and the output is x sub zoh of t. Okay. So this is the block diagram, which is in fact the block diagram for the mathematical model of the sample and hold approach, because although we obtain x sub z o h of t from x of t by very simple means, by using a simple hardware, just for sampling and holding that sample as a constant value for the following ts time units. Although this is done in a very simple or straightforward way, we want to represent x sub z o h of t in terms of xs of t, because we know that from xs of t we are able to obtain x of t back by means of a simple ideal low-pass filter with cutoff frequency omega s over 2. Of course, provided that we have no aliasing, that means omega s is greater than 2 omega m. Okay, so the next question is, can we reconstruct x of t from xzoh of t? So let us ask the question here and try to answer the question next. Can we reconstruct x of t from x sub zoh of t? Okay, so let us try to answer this question. Okay, now we are trying to answer the following question. Can we reconstruct or retrieve the original signal x of t, the band-limited signal x of t, from xzoh of t, that means the signal we have obtained by the sample and hold approach. Now, first of all, let us remember the LTI system we have used in the sample and hold signal model. Okay, the LTI system used in the sample and hold approach has the impulse response h of t, which is equal to 1 for t between 0 and ts and 0 otherwise. Okay, so the Fourier transform of h of t is the frequency response. So the frequency response h of omega is the Fourier transform of h of t. So it is from minus infinity to plus infinity h of t e to minus j omega t integrated with respect to t. So this turns out to be from 0 to ts e2 minus j omega t integrated with respect to t. So it is e2 minus j omega t divided by minus j omega evaluated at 0 and ts. So this turns out to be 1 minus e2 minus j omega ts divided by j omega. So this can be h of omega can be reduced to the following form. In fact, it is a shifted well, we have the rectangular pulse, and we know that the Fourier transform of a rectangular pulse is the sinc function. But here we have a shifted rectangular pulse, so we will have the additional phase shift as expected. Now, h of omega can be written as, let me write it over here. H of omega is, we can take e2 minus j omega ts over 2 as the common term outside. So we have e2 j omega ts over 2 minus e2 minus j omega ts over 2. And we have in the denominator, we have j omega divided by this entire expression, j omega. So it is equal to e2 minus j omega ts over 2. So the term in the numerator is 2 times sine omega ts over 2 divided by, we have in fact also j, 2j. Divided by j omega. J's will cancel out. Let us do the following. Multiply the numerator and the denominator by ts over 2. So we have e2 minus j omega ts over 2. So we have sine omega ts over 2 divided by omega ts over 2. We have 2 here, and we have ts over 2 as well. So 2's will cancel out. So we have ts e2 minus j omega ts over 2 sine omega ts over 2 divided by omega ts over 2. So this is the frequency response of the system, LTI system we have used in the sample and hold approach. Now, let us assume that the sampling frequency omega s is greater than 2 omega m. Therefore, no aliasing case. That means the shifted replicas of the spectrum of x of t, the Fourier transform of x of t, the shifted replicas of the Fourier transform will not overlap. So we will be able to obtain the original signal by low-pass filtering. But in order to do that, from the signal x sub ZOH of t, we have to obtain xs of t back. So if we can do this in the reconstruction phase, if we can obtain xs of t back, we will be able to use the ideal low-pass filter to extract the Fourier transform of x of t, that is x of omega, and therefore x of t is retrieved. So, if we can obtain xs of t from x ZOH of t, then we can use an ideal low-pass filter with cutoff frequency omega c equal to omega s over 2 to retrieve x of t. Okay, how can we do this? Now let us look at the details of this step of our calculation. Okay, we know that x ZOH of t is xs of t convolved with h of t, the rectangular pulse. So in frequency domain, capital X ZOH of omega is equal to xs of omega h of omega. Okay. Now, if we can obtain xs of omega from xZOH of omega, this is clearly obtained by means of a division with h of omega. However, we have to be careful with such operations because h of omega is expressed in terms of a sinc function which has zeros. So at those zeros, the division is not defined. However, we are not going to, we do not have to deal with such problems as we see in a minute. Now, if we can obtain xs of omega, then x of omega can be obtained as, so we have xs of omega, and we have the ideal low-pass filter with cutoff frequency omega c, and in fact, let us show the impulse response or frequency response of this ideal low pass filter by H LPF of omega. We are going to obtain X of omega. Now, remember that in our previous discussions related to sampling, Shannon Sampling Theorem, HLPF of omega is equal to Ts for absolute value of omega less than omega s over 2. So the cutoff frequency is omega s over 2 and 0 otherwise. Okay. Now, in fact, if we start with XZOH of omega, now if we feed it to the system whose frequency response is 1 over h of omega, we are going to obtain XS of omega. However, here we have the rather difficult operation of division. We have to define 1 over h of omega. In order to avoid these difficulties, we can combine the frequency response of the ideal low-pass filter and the frequency response we have defined here as 1 over h of omega as a single system, which is in fact obtained by cascading this system with the ideal low-pass filter. So, in a way, we do not like this approach or notation, but we can start with XZOH of omega, and then we use this as the input signal of a system whose frequency response is HLPF of omega times 1 over h of omega. Okay, and the output will be now when we apply 1 over h of omega as our system, we obtain excess of omega, and from excess of omega by low pass filtering we are able to obtain x of omega. Okay, so we are able to retrieve x of t, in other words. But what is HLPF of omega multiplied by 1 over h of omega? It is equal to, now we know that the low pass filter has the frequency response which is non-zero only in the interval from minus omega s over 2 to omega s over 2. So it will be Ts multiplied by 1 over h of omega. So it is omega Ts over 2 divided by there is also a Ts as the multiplier, sine omega Ts over 2. Okay, we have a multiplication here. Therefore, these two terms will cancel out. For magnitude omega, absolute value of omega, less than omega s over 2 and 0 otherwise. Oh, I have forgotten the phase term. We have also e2 j omega ts over 2. Okay. So magnitude of this system whose frequency response is given by means of this expression, we can just draw the magnitude and phase graphs of the system. Okay, the magnitude graph of h LPF of omega divided by h of omega is, okay, it is only non-zero in the interval from minus omega s over 2 to omega s over 2. Okay, when omega is equal to 0, we have 1, as you see. We have sine of 0 divided by 0. We have the same expressions, as you see, omega ts over 2. When omega is equal to 0, sine omega ts over 2 divided by omega ts over 2 is equal to 1. So it passes through 1 here. So this is the point 1. Now when omega is equal to omega s over 2, we have here in the denominator sine pi over 2, yes, which is equal to 1, and here we have pi over 2. So pi over 2 is greater than 1. So the frequency, the magnitude of the frequency response will have such a characteristic. Okay, so this value here is pi over 2. Now, on the other hand, we have the phase graph. Okay, here we have a phase of, okay, we have magnitude of this frequency response drawn in this way. The phase of h LP f of omega divided by h of omega is simply omega ts over 2. So it is at omega s over 2, it will be equal to pi over 2, and at minus omega s over 2 we will have this is minus omega s over 2, we will have minus pi over 2. So it will be such a linear graph for the phase. Okay, so now, in order to summarize what we have done in this model for the sample and hold approach, the sample and hold signal, which is x sub ZOH of t, can be obtained very easily by means of the sample and hold operation. So it is a physically realizable signal. Okay, but still we have used the impulse train signal model in order to be able to use the theory we have developed for the Shannon Sampling Theorem. However, in the reconstruction phase, we have to, since we are starting with the signal x sub ZOH of t or ZOH of omega in frequency domain, we have to use this filter with this magnitude characteristics and with this phase characteristics in order to be able to retrieve the signal x of t back from x sub ZOH of t. Okay, thanks for watching.